All right, so let's define what elastic and inelastic means. So it's defined right here. So first we have to have a system, right? So we're going to define what our system is. So we're going to isolate the objects, and we call it an isolated system. So what that means is that you have two objects, right? You have two objects, and you're going to look at the exchange of momentum between the two objects, and you're going to ignore the external forces. Okay? So like friction, like air resistance, things that are outside forces. So let's say you have two balls that are colliding, that are coming together, right? One going this way and the other one's going this way, and they're about to hit. So this is a collision. Your system then becomes, what are the forces happening between the two? That's all you're going to include in your isolated system. So we have to define that. So we're not going to worry about friction with the surfaces. We're not going to worry about air resistance. Okay? Now, if you have, let's say, two objects here that are colliding, and they just bounce off after the collision. So after, this one goes this way, and then after, the other one goes the other way in the opposite direction, you will say that's an elastic collision. Now, in reality, though, you don't have 100% elastic collision. Like, remember, I used the example of a ball. Even though it bounces off, we consider it elastic. It's not 100% elastic because some of that momentum went into the floor and it's lost as heat, right? You won't be able to detect this, but every time things collide, like when I clap, just one clap, you probably will actually see the difference. When you clap, you will feel that your hands become warmer. And that was just one clap. Go ahead, do that. Collide your hands. So one clap. Do you feel warmer? Yeah. Okay, so your momentum of your right hand and the momentum of your left hand colliding, okay, well, they don't bounce back. So would that be elastic or inelastic? Inelastic. That's an inelastic collision. So that's by definition inelastic. They get stuck together because you're making them stuck together. And also, the definition of elastic and inelastic is that the transfer of energy. Is the energy conserved? So in this case, that would be lost in the form of heat. So your hands become warmer. That means the momentum, the m times v, now is converted some of it into heat. So that would be an example of inelastic collision. Okay?
Elastic, you mean now it will be the ball that it's like going up?
Yeah, so inelastic will be they come together and damage is done, and not they may move, they could move,
But not more.
not so much, not the original one. So elastic collision would be two billiard balls, for example, and they bounce back off. That's a good example of elastic collision.
So I have a question. So both the hands, they're coming together, but they're not like colliding or making any.
Yeah, there's actually light that will be produced, very small. We can't even see it. But yeah, there's a little bit of a spark, and there's a little bit of heat produced from that. So those energy being lost to the system is an example of making it an inelastic collision because energy is lost. So same way that cars colliding, you have some damage, that's inelastic.
So it can either make damage or not damage.
Not necessarily. There doesn't have to have a damage,
Okay.
right? So for example, if I take a ball or a rubber eraser and I drop it, right? Oh, it still bounced. But if you have something and it doesn't bounce, here, okay, so it bounced only a little bit, right? That would be elastic or inelastic at the point of collision?
Inelastic.
What do you think?
Inelastic.
Inelastic? Why?
Because it's not moving on.
But
It bounced.
it bounced. So the fact that
It's
it
not
bounced and they
moving.
separated, that would be elastic collision.
Elastic or inelastic?
Elastic, because it bounced.
No, so what happened in my
It still bounced.
If it's elastic, let's say if this one to be that,
Yeah,
if going more.
that's right. That would be elastic.
Inelastic.
Inelastic would be-
Let's like that.
Yes, so right here, there, that's an example of an inelastic collision. It just went straight into the floor. It stayed together. This one, if it bounces off, oh, that
No,
one,
it went like it could
Yeah.
first time. So that's
the first time it flipped, right?
So it doesn't matter how was the damage.
Doesn't matter even if there's no damage. That's right. Depends on whether they split up or not. They stayed together. So that would be the easier way to look at that, okay? So collisions are often classified according to whether the total kinetic energy changes during the collision. What is kinetic energy? So let's define those things. I know there actually is a different unit. So we're going to have a potential versus kinetic. We're going to explore this in our next unit. So potential versus kinetic. What is the difference? Just a quick jumping ahead to the next unit. Okay, so which one is moving? Kinetic is the energy of motion, right? So that means it's already moving. Once it becomes in motion or it becomes kinetic, the potential becomes less, right? So it's a balance between potential and kinetic. Potential energy is called the stored energy and it's not used yet. So that means it's not being used. So we'll explore this in more details later on, okay? Okay, so we'll read that. We'll get into that more. So now here's a definition. An elastic collision is one in which the total kinetic energy of the system after the collision is equal to the total kinetic energy after or before the collision. I'm actually going to define this in terms of momentum now. Momentum, energy, they're both conserved, right? So here's what happens. So in terms of momentum of collision, so you have your momentum. We're going to call this the total moment. Can I just call it P? P for momentum. The total momentum of the system before the collision is actually going to be equal to the total momentum after they collide. So we're going to put this in a symbolic way now. You guys remember when I used this symbol? So what does that mean? Sigma. Sigma means net, right? So that's the net momentum before. So we can call it initial, I, is equal to the net momentum final of the system. We're talking net. We're talking the entire system right here. So if you have two masses colliding, that means the momentum of the first one plus the momentum of the second one will equal to those two combined together after they collide. Okay? This is also known as the conservation of momentum. So that is what an elastic collision is. So conservation of momentum. Okay? So an inelastic collision is one in which the total kinetic energy of the system is not the same before and after the collision. If the objects stick together after colliding, okay, so they stick together, the collision is said to be completely inelastic. Okay? So inelastic, just to summarize now, I'm going to summarize both here. So the elastic versus inelastic. The objects, here's the summary, stick together. So you drop an object, it doesn't bounce, that will be inelastic. Okay? Elastic collision would be the opposite then. The total kinetic energy of the system is the same before and after if the objects then don't stick together. So you could say the objects not stuck together. It's an example of elastic collision. Okay? So, of course, that is ignoring the effects of friction with the air. That's why balls never go back up. So it's not 100% elastic. You have to realize that, right? Because in reality, in the real world, okay, some of that momentum, when you drop a ball, is going to be transferred to the floor, okay, in the form of heat, some sparks. So it's not exactly 100%. There's no such thing as 100% elasticity or 100% efficiency. So it is important to realize that even though the kinetic energies of the individual parts of the system may change, the total linear momentum may be conserved. Okay, so even though you have an inelastic collision, the total linear momentum may be conserved. So for example, when two skaters are stationary, not moving, the initial kinetic or momentum is 0. But when they push each other, they acquire kinetic energy because work is done. Okay, so the internal forces cannot change, is conserved. Okay, so basically we're looking at conservation of momentum. This is the most important part on this page right here. Put it in a box. So this is what we're looking at. Momentum before is equal to the momentum after, total for both. Okay, before and after. Okay, so let's take a look at some examples now. So that's our main concept. It's called the conservation of momentum. One of the few things in our universe that is conserved. So a completely inelastic, we're going to start with inelastic. Do you guys remember which one gets stuck? Do these things get stuck? Inelastic. Okay, so inelastic, the objects will stay together. Okay. Completely inelastic collision occurs when two objects stick together. An example of this would be two colliding balls of putty. Okay, so putty, not metal balls. Okay, let's take a look at some example here. To be more specific, a railroad car of mass 10,000 kilogram traveling at a speed of 24 meters per second strikes an identical car at rest. That can't be good. No one's inside, no one's gonna get hurt, okay? The cars locked together, so you know then it's been defined as inelastic. So we want to determine the common speed afterwards. All right, so I wish I left this blank and just work it from scratch. Okay, so maybe I should do that. Can I do that and work? Or is it's just already here? It doesn't matter. So you're looking for the common speed. What does that mean, common speed? It's the same, right? Because they are stuck together, they're gonna have the same speed because they're moving together as one big mass now, right? Combined. So it says here, identical car at rest. Okay, we're actually looking at a truck, not a truck, a railroad car, not a regular car. So I'm gonna call this one mass 1. The second one, the identical car, is mass 2, and it's gonna be the same mass. Okay? Can you guys tell me what is the momentum of mass 2 before they collided? Before, yeah, the identical car, this one right here. What is the momentum? 0 because it's at rest, right? So we're gonna now take a look at the initial momentum initially is equal to the initial momentum final. That is always gonna be where we start. So let's now combine this. I'm actually going to do right here. Okay, I'm gonna ignore this one for now. Okay, I'm gonna actually ignore this one right here. The kinetic energy I'm gonna deal with later. Okay, so here it is on the bottom. Momentum before is equal to the total momentum final. Okay, now how many objects are colliding here? We have this car going this way, the train, they're called railroad cars, and it's going to collide, right? Actually, this is at rest. The first one is going towards mass 2. At rest. That's our situation, right? So only one arrow. Does that make sense? Okay, so we're gonna call this M1 V1 initial plus M2 V2 initial is equal to the M1 V1 final plus M2 V2 final. So that's our equation right here. That's the formula. Because momentum is mass times velocity, right? And you have two objects here. So you're going to find the sum of both of them before they collide and after they collide. Make sense?
So you can use either of these equations, right?
This is always going to be the equation for any momentum that you're going to see. So here you have two objects, mass 1 and mass 2. So we're going to have mass 1 and mass 2.
My mass 1, velocity 1.
Yeah. Initial. So the initial momentum, this is what is the initial momentum, the sum of that is equal to the net final momentum. That's what that means. We just broke it down into individual M1 times V1 and M2 V2. Okay? But this is going to be your formula always. You have to remember this. I'm not even going to tell you that on your paper. You just have to know that that is a concept. Momentum before, the net momentum before is equal to the net momentum after the collision and explosion as well. Okay, so let's write down the numbers and then figure out first, what are we looking for in this question? We're looking for the V of them moving together, right? So here is what happens, just so we know what's happening here. They are identical, right? Can I borrow a, here, calculator? I want to see two objects that are identical. Okay, I'm going to take these two markers. That's fine. Here we go. Here's a railroad car, and it's moving, and the other one's at rest. So the other one hits the first one, the second one. The first one hits the second one, like that, and then they move together. That's what happens, right? This one is just sitting. This one hits it, and then they move together. This is what happens. So you know that the V is going to be the same. So I'm going to actually go and write down here. I'm going to isolate the V because that's what we're looking for. And I'm just going to put, that's the V final, M1 plus M2. Would that be okay for me to jump to that step? That's what that means. Because the V1 final is equal to the V2 final. That is what we know. Why? Why are they the same speed? Or I should say same velocity. Why? Because look, the first mass hits the second mass, and then what do? They move together. So their speed, the V1, is going to be equal to the V2 after they collide. Okay? So what? You got rear-ended before, right? So you were going with your speed. You had your momentum. The car behind you had their own momentum. When they collided, what happens is they move together. That's what happens in an inelastic collision. They move together as one big object. So what I did is I combined the mass. This is now just the math. I combined the masses and I isolated the V because V1F is equal to the V2F.
This one is the same final velocity.
Because they are moving together.
It depends on equations or always.
It depends on the situation. In this case, it's been defined that they move together as one. Okay?
They do that in the equation like that equation. Did they explain it?
Yeah, this is actually going to be the same equation all the time. That one right there with this asterisk. Momentum initial total is equal to the momentum final total.
That's okay. My question
Always.
is the,
This is not always the same equation. This only applies to objects that are moving together. They move together. Okay, so now we can actually write down the numbers here, right? Does the first car have a momentum? Yes, it does. What's the mass of the first car? 10,000. What was the velocity of the first car? 24. Okay, now we're going to add that to the second one before they collide. What was the momentum of the first car? 0. So don't even bother writing down the 10,000 kilogram mass. Times 0, it's still 0. Okay, so what are we looking for? VF. So now the rest is just the math, right? So isolating the VF, we now have 10,000 times 24, and then divide that by the total mass, right? So this is 24,000 divided by how many kilograms is their combined mass? 20,000. So the answer is 12 meters per second, and I'm just gonna say it's gonna go in the forward direction, whatever direction the first mass is going. There you go. So the answer is 12.